Let's consider now a circuit where we have all three: a resistor, a capacitor, and an inductor connected to an AC source. Now, one thing that's comforting is Kirchhoff's voltage rule is always true. That's for any instant at any time, the voltage across the generator minus the voltage across the inductor minus the voltage across the resistor minus the voltage across the capacitor is equal to 0. That's always true. Now, if we look at this is a particular simulation where we have R, C, and L connected to a generator. Okay, now we are getting all voltage values. VAC in black here is the voltage across the generator. VC is the voltage across the capacitor. VR is the voltage across the resistor. And the green one, VL, is the voltage across the inductor. Notice here this curious thing. When you look at these curves, the vertical scale is for voltage. The maximum value here is at 200 and we have minus 200 here. And we are spanning a time period of about 25 10 to the minus 3 seconds. Now we have a frequency of 100 Hertz here. Okay, pay attention to this. Look at the red curve, how it looks bigger than everything. So the red curve is the voltage across the capacitor. So what this tells me, VC max is bigger than any of the other Vmaxes. The smallest in this particular case is the blue one, VR max. Okay, the green one is not far different. That's VL max. Remember, the amplitude of each one of these is the Vmax. Now, the black one is the voltage across the generator. And from what we looked at a few minutes ago, the voltage across the generator is supposed to be the sum of all three. So what does that mean here? That means if we look at a particular instant, for example, this instant, that corresponds at a time of 9.78 10 to the minus 3 seconds, as you see it in yellow there, and we are reading a value for voltage as 42.9 volts. We are reading that value for both VL and VR since they intersect at that point. You know, of course, bearing the precision of the data gathering method I'm using right now, which is using a pointer and trying to estimate that I'm placing the cursor over the curve. Okay, so what we have here, 978 for time and 429 for both VR and VL. Okay, now if I go down here and try to find the time 978, okay, so we are here at 978, and that's given me minus 14 volts. This means now, if we try to find the voltage across the capacitor, we can do a little calculation and then we can check it back. So what we have for this particular time, this instant, which we said it is 9.78 10 to the minus 3 seconds. That's my t. Now, for that particular time, we found VL to to be equal to 42.9 volts, VR to also be equal to 42.9 volts, 42.9 volts, and VG we found it to be minus 14 volts. So this tells me that I should be able to find VC as equal, VC at that particular time, it should be equal to twice 42.9, that's 85.8 plus 14, so that's 99.8 volts. That's what I should get if my calculations are correct. Okay, now I go here, go back here and try to find it. So here for 9.78 10 to the minus 3 seconds, you notice that the voltage across the capacitor is minus 97.5, which is close enough to the value within experimental errors to the value we calculated. So this is what we mean by the sum of the all voltages is equal to 0. But as you notice, that's not easy. So this is what we are talking about. That's what we just had in the graphic. Okay, you can find the simulations here. Now, like we did for inductors and capacitors, we can define a reactance of all devices at the same time, meaning the combined reactance of an inductor, resistor, and capacitor. In this particular course, we are sticking to a simple circuit where we place these components only in series. Like we have them here, we can have an L and R in series, an R and a C in series, an L and a C in series, or all three in series like we see them right now. Now, when we have these particular devices in series, L, R, and C, their total reactance is going to be given by this expression, square root of R squared plus XL minus XC squared. Okay, we'll explain why is it the case a little later. And then, if we use the reactance expression, we can use it like we used it previously. So for example, for the case of the generator, Vmax is going to be Imax through the generator times that total reactance. And that total reactance, we also call it impedance. Now, a couple of things to note. This is always true. This is not. This is not either. The maximum values of the different components, they do not add up to the maximum value as we have seen in the simulation due to the generator. One last thing here. Okay, if we have here the total reactance, one might ask, what about how the current relates to the voltage in terms of, is it going to lead, lag, or is it going to be in phase for the case of the generator? Actually, that's going to depend. The voltage sometimes leads and sometimes lags. That depends on the frequency and the values of L and C. However, the reactance itself, its dependence on the frequency, it's a combination of the dependence of XL and XC. Remember, this is the dependence here of XC, and then we have the dependence, a linear dependence of XL. The combination gives us this kind of a graph. The dependence of the current as a function of the frequency is going to look somewhat like this. So you notice it kind of peaks at a particular value. We'll get back to that later on. In summary, for an RLC circuit in series, we can use Kirchhoff's rule for any time, for any instant, but for RMS or maximum values, peak values, we have these expressions. For voltage, VR max is going to be I max R, or VR RMS is I RMS R. And we have a similar expression for VC, but instead of R, we have the reactance XC. Similar expression for L, so we have XL instead of XC, or instead of R. Similar expression for V across the generator is going to be I max Z, where Z is the total reactance or impedance. Remember here, omega is 2 pi times F. It's the angular frequency.